hopefully today finish chapter 1, and then when we dive into chapter 2, we'll get into some applications and things like that of derivatives. Okay, wanted to make sure first off in section 1.7 which talks about the chain rule, that's working for you. We had talked about with the chain rule, what you're going to have is a function inside of a function. There'll be an outside function and there'll be an inside function. So for example, we have something like y equals the square root of 4x squared minus 18x. The first thing to remember here is you cannot break this up into two separate pieces. Folks are sometimes inclined to rewrite this as the square root of 4x squared minus the square root of 18x. Okay, folks are tempted to do things like that, but that's not true, is it? Okay, it has to all be left as one common square root. The only way you can separate it, is if the stuff inside is being multiplied together, not added. Okay? And subtraction is a form of adding. Okay? All right, so how do you take the derivative of something like this? Well, the first maneuver is to rewrite it as an exponent. So this will all be to the 1/2 power. Why do we not need the negative with the exponent? We just did to the 1/2. Why isn't it to the negative 1/2? What's the negative tell you? It's in the denominator. Okay? So the negative only tells you if it's numerator or denominator. The 1/2 tells you it's square root. If we're going to take the derivative of this, we've got a function 4x squared minus 18x. That's a function. You could take the derivative of that by itself, couldn't you? Okay. But it's inside of another one. It's inside the square root thing. Okay. So you have a function inside of a function. Does that make sense to everybody? It's also what is called a composite function. You may have seen these back in ancient times where you had things like h of x equals g of f of x, where it talks about a function being applied to another function. Or this could have been written as g of f of x, like that. Does that look familiar? Or even more frequently without the x part on it, like that. So there's a couple of notations. First thing you need to realize, this is a composite function. It has an outside part, it has an inside part. When you do chain rule, it's kind of like unwrapping a present, isn't it? You just do the outside part, and when you're working on the outside, does the inside change at all, or does it stay the same? It stays the same, doesn't it? Okay. So what's going to happen first is we're going to take the derivative of the outside, which is going to give us 1/2 and a negative 1/2. Does that make sense how we've done the derivative of the outside there? Now that we've done the derivative of the outside, do we put the 8x minus 18 inside? No, 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 no. Because when you're working on the outside, you leave the inside alone. Okay? You only work at one level at a time. Okay, so if we're working on the outside, we leave the inside alone. After you've finished working on the outside, then you come back and you do the derivative of what's inside. You could leave the solution like that, or folks are often wondering about how far should I go on simplifying. If there's something easy to do, pick that off. Otherwise, just leave it alone. In this case here, we have the 1/2 times this whole thing times that. we could reorder it so that we have the 1/2 times that. And 1/2 of that's going to give you a 4x minus 9. Does that make sense to everybody? Times the 4x squared minus the 18x to the negative 1/2 power. And that would be your answer. Now, one of the things to be mindful of is when we're taking derivatives, derivatives are slopes. Derivatives talk about how things are changing. If this was a cost function originally, so let's just make something up here. Let's pretend that this was a cost function. The derivative would be telling you how the cost is changing, wouldn't it? When you get into economics, there's a phrase for that. It's called marginal cost. Does that make sense to everybody? Maybe sound familiar to you if you've had a business course or two? If this was a cost function, at this point you could be asked a couple of questions. One, if x equals 18, well, let's say 10 units, make it something easy. If x equals 10 units, what is the cost to make 10 units? Well, what equation would you plug 10 into to get the cost for 10 units? Ooh. This is where things start to get a little less comfortable for folks. Well, let's see, if we want cost, we're going to go to the cost function. That's the first one. So if you want to know the cost of producing 10 units, you would plug x equals 10 into that first formula. Does that make sense? Now, here's where things get a little bit trickier. If we were looking at changing our production from 10 units to 11 units, we were going to make one more unit. Let's say these are dump trucks or buses or something like that, where one unit is pretty big. And making one more is a lot more significant than just making one more pen. And we wanted to know how much will the cost change if we move from making 10 of these things to making 11 of them. That's when you go to the marginal cost function. The marginal cost function tells you how much it will cost to make one more unit. And you've got to be careful. Okay? If we're making 10, we're making 10 units and want to know the cost to make an 11th unit. Does it make sense what's going on here? Okay, let's say you work, I don't know, Sterling, Mack, GMC, somewhere or other where they manufacture dump trucks. Currently, you turn out 10 trucks a day. And you're presented with a new contract, but it means you got to come up with 11 trucks a day, which you can do. Okay, everybody just works a little bit harder, a little bit faster, and you get it done. Fill the contract, and everybody gets a bonus, and they're happy. How much is it going to cost to make that 11th truck per day? There are a lot of costs involved with making an 11th truck. Okay, the extra materials, you know, all kinds of stuff factor into making an 11th unit. But to make the 11th unit, be really careful. Watch what you do. You take the derivative and you don't evaluate it at 10 or at 11, you evaluate it at 10. Because what this slope does is it tells you how much of an increase you have from 10 to 11, which is the marginal cost. How much additional cost is there to make an 11? Well, the slope at 10 tells you how far up you got to go to get to 11, doesn't it? Which is really what we're asking here in another way. Okay? To make the cost of 11th unit, what you want to do is evaluate this. And be really careful. One of the most common mistakes people will make is they'll do the derivative and then they'll put 11 in. They'll evaluate it with x or q or whatever the variable is equal to 11. But the catch is when you put 11 in, that tells you the cost to make what? The 12th unit. So you're 1 unit off. Does that make sense to everybody? So you want to be careful what's going on when you take these derivatives. Let's take a look at another chain rule. So we're mixing in a couple of things here. First, chain rule. Second, going over some marginal cost type stuff. Okay. Let's say that we have something like this. Say we have y equals the sine of 3x squared minus e to the x. First thing to realize is this is not a product rule. It's good to see you. This is not a product rule, is it? Because it's not sine times the 3x squared minus e to the x. Okay, it's not sine times that. Does that make sense to everybody? You okay with that? It's sine applied to. So this is not a product rule. This is going to be chain rule again. When you go to compute the derivative, first thing you do is you only take the derivative of the outside and you leave the inside alone. Well, what's the derivative of sine? Cosine. So we're going to get is the cosine, leave the inside alone. Then you take that whole thing times what? Derivative of the inside. You got it. And the derivative of the inside is 6x minus e to the x. Remember we talked about doing a derivative of e to the x and its derivative is e to the x, and we went through that the other day with the Taylor series expansion. I said, yeah, that might be fair game on a test or a final somewhere. You're done. Does that one make sense to you? Okay. Our chain rule problems getting fairly comfortable. We took a look at a few of them the other day, took a look at some of them here. Okay. Are you okay? Okay. Where we're headed in section 1.8 is what's called higher order derivatives. Now, you can take the first derivative of a lot of stuff now. Okay. All kinds of stuff, with sine, with cosine, with tangent, with e to the x, with square roots, with natural logs, with polynomials, and rational functions. You're good for all kinds of stuff. Okay. However, what's going to wind up happening is we need more information. If, for example, we start out with something like y equals 12x to the fifth minus 7x squared plus 8. What we can do is we can compute the first derivative. The first derivative is going to give us 60x to the fourth minus 14x. Remember, this is going to be a couple of things. This is going to, first off, tell us what's the equation for the slope anywhere original function, right? I think everybody's pretty well got that down at this point. Secondly, it's going to allow us to locate max-min points. How do you locate max-min points? You set it equal to 0. Real fair question for the final. Why do you set the derivative equal to 0 to get your max-min points? What's so special about 0? Why not 1? Or 10? Or e squared? Common answer I get back is because it's easier to solve. Okay. Well, that is true, but that's not the reason. Okay. Just a quick reminder. If we have some kind of a function at a maximum point, here's a maximum point. At that maximum, what is the slope of the tangent line? 0. At a minimum point, there's one. What's the slope of the tangent line? 0. At any maximum or at any minimum, the tangent line is going to have a slope of 0, isn't it? That's why you set the derivative equal to 0. Not because it's easier to solve or anything like that. It is true it's easier to solve, but that's not why 0 works there. Okay, so with the first derivative, we can find these max-min points. If you'll recall, I've told you by January we're going to be headed into territory where you can't graph things anymore. Graphs are gone. Because we're going to be in 5, 6, 10 dimensions. Okay? Go over to the bookstore and try to buy 10-dimensional graph paper. Okay? What we're going to need is more information. We're going to need to be able to compute the second derivative. You can already do that. Guess what the second derivative of this is? Well, gosh, Chuck, I'm guessing it's going to be 4 times 60. It's x cubed minus the 14. Ta-da! Second derivative. There it is. Okay, you've got it. What are you going to do with it? I don't know. What the second derivative is useful for is to determine concavity. Concavity, what's that? Is that those things that you go to the dentist and get filled? Oh man, I got concavity in my tooth. Oh, it's close, it's a cavity. Okay. Concavity talks about, is the graph curving downward or is the graph curving upward? If you take a look at this graph that we already have here, in this region here, okay, is that thing concave up or concave down? Down. The curve points down, doesn't it? This section here is concave down. If we move over into this next little section, this section here is concave up. This is going to be really handy when we can no longer see the graph, because we're going to use the second derivative to determine if it's concave down or concave up. Now, if it's concave down, what do you have? Max or min? Maximum. If it's concave up, what do you have? Minimum. Which kind of runs opposite to what you might expect. A lot of times people are thinking up is max and down is min, right? Well, not in this case. What what winds up happening is, if you're, and save some space to the left of this, because I'm going to, bless you, come back in a minute and throw some more stuff in. Concave down means that you have a maximum. Concave up means that you have a minimum. Concave down occurs when the second derivative is less than 0. The second derivative greater than 0 means you're concave up and at a minimum. Well, how do I know if it's a max or a min? What's going to wind up happening is we're going to go through a whole series of steps. For example, suppose you were given a cost function and you were asked to optimize that. Does optimize mean to maximize it, minimize it, or what? Well, it depends on the situation. With cost, the ideal cost is max or min. Minimize, right? You got to let the context define for you whether we're maximizing or minimizing. Okay, so if it's a cost function, you would take the derivative, set the derivative equal to 0, and that'll give you some of each. Maybe some maximum points, some minimum points. Then what you have to do is go back through and sort them out. Okay? Let's take a look at something like that. Because what's going to happen is you're going to have to be able to sort this stuff out, and then after you sort it out, figure out if what you have there is a maximum or a minimum. Here we go. Let's take a look at an example like this. Let's say you're given a revenue function, and this revenue function works out to be a negative 50x squared plus 500x plus 30,000. Okay? This is revenue. Be careful. Do you want to maximize or minimize revenue? Yeah, hopefully going into business, or you may be thinking, well, I'm going into pharmacy. Well, I got news for you. You're going into business, because if you don't sell the medicine, you don't have a job, and selling it is business. Okay? Wherever else you're headed, ultimately you're going to be somewhere where they're going to pay you, right? That's a business. So regardless of what direction you're headed, you're going to be in business. Okay, so revenue. We want to maximize it. How would you maximize this? Well, what is the first step to maximizing? First step is to compute the derivative, right? Okay, so if we compute the derivative of this, well, the derivative of this is pretty easy, isn't it? It's going to be a negative 100x plus 500. Step 1, compute the derivative. Okay, I've got the derivative. What do we want to know about the derivative? Where it's equal to 0. So then we're going to take this negative 100x plus the 500, set it equal to 0, and do you see that in the end x equals 5? Move the 100 over to the right-hand side. So you have 500 equals 100x. Divide both sides by 100, and you get x equals 5. Does that make sense? Now we got to be careful. We've got to make sure that this is a maximum, not a minimum. What's going to happen if you're minimizing revenue? What's going to happen to your business if you minimize the revenue? What is revenue? What's revenue? It's the money that comes in, right? If you minimize the money that comes in, that means your company's not making any money, which means you're going to get hungry really fast. Okay? So we want to maximize it. We want to make sure we're going to maximize this. So the first step we do is we compute this. This is an optimal value. Optimal could be maximum or minimum. So the second step we need to do then is to verify it's a maximum. Verify x equals 5 is a maximum. Because if we set this company up where we're minimizing revenue, you're going to get hungry very fast. Okay, so to check for a maximum or a minimum, see what's up here in the blue, right here. Don't need to go up any further than that. We're going to do the second derivative. Now tell us if it's concave up or concave down. What we're going to do is we're going to compute the second derivative. And the second derivative of this one's pretty simple. The second derivative is just a negative 100, isn't it? It will, in some cases, just come out to be a number. In those cases, you've got things easy. The 100 is less than 0. If it's less than 0, if it's less than 0, is it concave up or down? It's concave down. And if it's concave down, you have a maximum. Remember, concave down looks like this. Okay? May sound silly. Here's how I remember it. If things are going negatively, are you smiling or frowning? Usually frowning, right? Frowning looks like this, right? And frowning, you wind up with a maximum. Going up to the blue, up at the top of the screen, if it's a positive second derivative, if things are going positive, you're usually smiling. Smiling looks like this. If it's smiling, you have a minimum. Okay? It's easy otherwise to get them mixed up. Okay, so with this, the second derivative just came out a number. The number's negative. We know it is concave down. We've got a maximum. So we know that this optimal value is a maximum. That comes from the second step. Why is it that the negative gives us a maximum? What we need to understand is what the second derivative is really telling us. If we go back to some function, let's say we have y equals x squared plus 5x plus 6. It's going to be a parabola. Hey, I'll show you something cool. Okay. There you go. How about that? Okay, it's going to be a parabola. It's going to go through, let's see, kind of like that. So there's our graph. Do you buy that the thing actually opens up as a parabola? Okay, the leading coefficient's a 1, it's positive, so it's going to open up. It factors into x plus 2 times x plus 3, so that means x equals negative 2 and x equals negative 3 are the roots. Okay. Hey, we've just rolled through a whole lot of stuff real quick, and you were there. Yep, yeah, no problem. You've got a lot of math. Okay. Take a look at what's happening here to the slopes. Think about what the slopes are doing. On the left side, the slope of a tangent line looks about like that, doesn't it? That's a fairly negative number, isn't it? That might be something like, and I'm just making something up here, might be the slope is negative 10. As you move a little further, you get something like this. This might be a slope of -5. As you move a little further, you get something like this, where you get a slope of, let's say, -1. Here's a slope of 0. Then, as you move even further, you get something like a slope of 1. And as you go further still, you get a slope of 5. Going from left to right, in what direction is the value of the slope moving? Is it moving in a negative direction or in a positive direction? It's moving in a positive, isn't it? Because you start with a value of -10. From -10, you go -5, 0, 1. Sorry, -1, 0, +1, +5, and somewhere then we get +10. The value of the slope is moving in a positive direction. That's what the second derivative tells you, is what direction is the slope moving in. It tells you how is the slope changing. If we take the derivative of this, we get 2x plus 5. And if we take the second derivative of this, we're going to get 2. Two's positive. Hey, if things are positive, you're smiling or frowning? Smiling, right? Oh, if you're smiling, we have a minimum. Oh, well, yeah, it's kind of what we got there. What the second derivative does is it tells you in what direction the slope is moving. I know I said that. I want you to catch it. Let's take a look at another example. Let's say we have a parabola like this. And we look at a series of slopes as we move from left to right on this. Slopes of tangent lines. This might be a slope of 5. As we move a little further, this might be a slope of 1. As we move further still, slope of 0. And as you continue on around, this is going to be a slope of something like -1. And then as we get steeper still, slope of -5. Do you see the direction the slope is moving in this case? It's starting at positive and moving negative. It's getting smaller, isn't it? This is a scenario where, if this is f of x, the second derivative of x is going to be positive or negative? It's going to be negative, isn't it? The slope's moving in a negative direction. It's going to be less than 0, which means that it's concave down, which also means it's a max. So realize the second derivative tells you what direction is the slope moving in. Make sense? Everybody good with that? Okay, so we will wind up, once we get into applications, we're always going to have 3 equations. We're going to have our function, we're going to have our derivative, which will help us find maxes and mins, then we'll have the second derivative, which will help us to determine if it is a maximum or if it is a minimum. Okay? Because when we get to step 2, all we know is it's something or other. It could be a high point, could be a low point, don't know what. Won't know for sure till we get to the second derivative. Does that make sense to everybody? Let's take a look at an example. A couple years ago, took the kids on a really cool vacation. Took Becky too. Okay. Went out to Yellowstone. Driving out there is 3 days of driving. 3 10 to 12-hour days of driving. It's a long drive from Cincinnati to Yellowstone. It's about 33 or 34 hours of driving. careful not to go too fast, right? Well, if you've never driven through there, you might be surprised to find that if you're doing 80 or 90 miles an hour, you're blocking the road and you're just going to get blown off like dust. Okay? We were filling up, and I got talking to a state trooper who happened to pull in. I said, "You guys drive kind of fast out here." He looked at the plate, saw how high, and he said, "Yeah, if you keep it under 100, we won't bother you." And that's literally the case. Everybody out there is doing around 100 miles an hour. Because the roads are straight, they're flat, you can see 13, 14, 15 miles down the road easy. Okay? So, we're driving. One day we get to the Badlands, and it's really amazing as you approach the Badlands from the east. You're coming along, and you got this prairie. And it literally is the case that all of a sudden it goes boom, and here it is, it's desert. And it looks like something from the moon. I mean, just boom, that abruptly, and there it is. Okay, so we hang out there for a day or so, do some hiking, have some fun. Find one of these cliffs, and the kids and I are looking over the cliff. Of course, as with any good cliff, you got to get as close as you can, right? If you're not scared, you're not close enough. Okay. And Becky is back here screaming, "Chuck, get him away from the cliff. What are you doing?" "We're looking." "Yeah, you're looking like you're going to get killed. Get away from that cliff." Well, there's nobody down here in the bottom of this thing. And the kids and I are looking, and we're wonder how high up this is. How high up are we? And they made comment to them, with a little bit of math and a rock, we can figure out how high up we are. At first they looked at me like, "Dad, really? You got to do everything with math?" I said, "No, really. Grab a rock, whip out your phone, put the stopwatch on, and we can figure out how high we are." Okay? So they're going along with this. Daniel, of course, wants to be the one with the rock, and Lauren's fine with the stopwatch. And the catch to this is you got to be really careful. You can't throw the rock. You start out, you just hold the rock like this, and you let go of it. It's very important that the initial velocity of the rock equals 0. And you'll see why here in a minute. So the deal is count 3, 2, 1. Let go of the rock, and as Daniel lets go of the rock, Lauren starts the timer. And as soon as it hits the ground, not when you hear it, but when it hits the ground, you stop the watch. And there's all the information we need to figure out how high up we are. Okay? And the kids are, "Really?" Well, you need one other little piece of information, and that's this equation. The height, and if you've had some physics, you know this one, negative 16t squared plus v sub 0 t plus s sub 0. Now, I'm not encouraging you to throw rocks off of cliffs. You can kill somebody like this. Okay? Especially at Kings Island. Don't do this off of the Eiffel Tower. They'll arrest you and throw you out of the park. All right, so we've got this equation. Anybody know what v sub 0 means? It's the initial velocity. Well, now wait a minute. I was real careful to explain to Daniel he couldn't throw it. So at the very start, what was the velocity of the rock? 0, wasn't it? Oh. Well, if the initial velocity is 0, hey, that's going to make this a whole lot easier now, isn't it? Because one of the terms just goes away. Do we know what the initial height is? No. This is what we want to figure out. Do we know what the height sometime later is? And the answer is, well, in fact, we do. The rock's laying down here. Compared to, well, what's its height laying down there? 0. Does that make sense? So we wind up with is this equation 0 equals a negative 16 times whatever the time is squared plus s sub 0. And then just looked over to Lauren and said, okay, kiddo, how much time rolled? And I forget exactly what it was. It was pretty high. It was something like 3.7 seconds. That's all you need to know. And you can figure out what the height is. What's the height of that cliff where we were? You can all do the algebra, can't you? And you can do it on your cell phone. I mean, we did it on our cell phone. You know those calculators they have. Okay, if you hold it this way, it's a simple calculator. You turn your phone sideways, and whoa, look how that opens up. And you got square roots and all kinds of good stuff. Well, let's see. If we do the 3.7 squared times 16 equals, that's about what it was. We're going to get 219.04 equals s sub 0. So about how high was that cliff? About 220 feet, which is about like a 22-story building. So it was a pretty good sized cliff. Okay, well that's nice, Chuck, but what does this have to do with anything that we're talking about here? What this first equation talks about is height. This is the height. If we take its derivative, s prime of t, we're going to get a negative 32t plus v sub 0. Does that make sense to everybody, taking the derivative of that equation? What happened to s sub 0? When I took the derivative, the s sub 0 disappeared. Well, isn't that the initial height, which is just a number? And what's the derivative of any number? The derivative of any constant is 0. It's there. It's plus 0, but who really cares? Now, what's this going to tell us? This is going to tell us how fast the height is changing. This is going to explain how is the height changing. It's going to tell us how fast the height is changing in feet per second. Oh, wait a minute. Feet per second is a measure of what? Speed. Wait a minute. You mean if I start with height and I take the derivative, what I have now is an equation for velocity? Yes, that's exactly what this is. This winds up being the velocity. This is the velocity equation. It tells you how fast the height is changing. And how fast the height is changing is its velocity, isn't it? Well, it's kind of cool. The kids were kind of curious that, well, how fast was that rock going when it hit the ground? And Daniel's first question is, could I kill somebody? Or he was like 10 years old, you know. Sticks, rocks, everything's a weapon of some sort. Okay, well, let's figure out how fast that rock was going in 3.7 seconds. So it's going to be a negative 32 times 3.7 seconds plus, what was the initial velocity? 0. Equals, well, if we take this and multiply it out, negative 32 times 3.7 equals 118.4. This is going to be feet per second. Is that very fast? I don't know. Sounds fast. But how fast is fast? Is this supersonic? Or is this 40 miles an hour? I don't remember, Chuck. to do anything like this before, you can always cheat and just go online and say convert 118.4 feet per second to miles per hour. Or, I always keep this in mind, 88 feet per second is 60 miles per hour. Is that rock going faster or slower than 60 miles an hour? Going faster than 60 miles an hour, isn't it? In fact, we could set this up as the 88 over the 118.4 equals 60 over x. Do you see the ratio we're setting up there? Now, how do you solve a ratio like that? Cross multiply, don't you? And what we're going to wind up with is this 118.4 times 60, equals 88x. So, I got to divide by the 88 now. And we get x equals about 81 miles per hour. So by the time that rock hits the ground, it's moving how fast? About 81 miles an hour. Would that hurt if it hit somebody? Yeah, that would leave a mark. Okay? Because he had a rock about the size of a softball. So it would be big enough for us to see when it hit the ground. He wanted to drop this massive thing. Nah, let's not. Okay, we're not trying to make craters here. All right. So the change in the height is the velocity. If we go a little bit further, we can compute the second derivative, which is just a negative 32. However, this second derivative tells you how the velocity is changing. Changing velocity. You've all experienced it. When you merge onto the expressway, what do you step on? I hope not the brake. Drives me insane when people slow down as they merge onto the expressway. It's a great way to create a massive wreck. Okay? What are you doing when you're coming on that merger? You are accelerating, aren't you? Your velocity is changing, isn't it? You're going from 30 miles an hour to 40 miles an hour to 50 miles an hour to 60 miles an hour up to about 65 miles. Oh yeah, as your velocity changes, that's called acceleration. This measures how the velocity is changing. This is acceleration. What's the negative 32? Well, this is feet per second per second. What? I've never seen units like that before. That's kind of weird. This is acceleration due to gravity. In the first second that something falls, if you start out at 0 at the top, 1 second later, it's moving downward at 32 feet per second. The negative means moving down. The next second, it's moving 64 feet per second. The next second, it's moving 96 feet per second. The second after that, it's moving, 96 plus another 32s and negative 120. Do you see that each second it's picking up another 32 feet per second? This portion right here means that every second it speeds up by that amount. Now, will things just speed up forever and ever if they are falling? No. You are familiar with that, with when people jump out of an airplane. Do they just keep going faster and faster and faster and faster and faster and then catch on fire and burn up because there's so much friction between them and the atmosphere? No. What winds up happening is it gets to the point that they can't accelerate any faster because the air is slowing them down now. That's called terminal velocity. Okay. So this acceleration does not continue forever. Unless you're in a vacuum. What we're after with these various derivatives is looking at, starting first off with some situation that we're looking at. The first derivative tells us how is the situation changing? How is the revenue changing? If this was revenue, the first derivative would be marginal revenue. How is the revenue changing? If it was profit, the first derivative would be marginal profit. And if it was cost, the first derivative would be marginal cost. The second derivative tells you how fast the marginal cost is changing. We won't need to go past second derivatives because in the applications we're interested in, beyond second derivative doesn't make any sense. It doesn't describe anything that we're after. Well, good. So you don't have to go any further than second derivative on anything. True. Okay. So that's good news. Some of the second derivatives will get a little entertaining. Okay. If, for example, you have something like this, y equals, let's say 3x squared plus 8 to the 87th power. Anybody want to multiply that puppy out? Want to FOIL that one out? Not so much. But the first derivative is pretty easy to do, isn't it? Because it's just a chain rule. It's going to be 87 something or other to the 86th power. Well, that something or other is going to be the inside stuff. Leave it alone. Then you multiply later by the derivative of the inside stuff. Can clean this up a little bit. 6 times 87 is going to give us 522. X times this 3x squared plus 8 to the 86th power. When you need the second derivative, what property or rule do you need to apply to this to get the second derivative? You are going to use the chain rule, but overall what's going on? The main event here is this thing times this thing. You got something times something, which means the main event's going to be a product rule. And then when you do G prime, you're going to need the chain rules. We'll play with some stuff like that on Wednesday. Okay? Folks, I hope you have a good day. I look forward to seeing you all on Wednesday.